So now that we've worked with first order integrated rate law, you might ask, well, is there a second order integrated rate law? And the answer to that is absolutely yes. So here's our reaction. We're going to presume this is second order. Let's go ahead and come up with a rate law for a second order reaction where A is the only reactant. And we've got rate is equal to K, the rate constant, times A to the second power. If we derive and integrate this, we get this for a second order integrated rate law, which says that the inverse of A at times T is equal to a positive KT plus the inverse of the starting concentration. Now, once again, if you'll notice, this is the Y, and this is equal to mx plus b. In this case, the y-intercept is the inverse of the starting concentration. X is still times t, that's still the x value. And then m, which is the slope of our straight line, is equal to the rate constant. And y, on the y-axis, we have the inverse of the concentration at times t. If I were to take a chance and do this drawing, I know there's an easier way to do this. This is the y-axis, which is 1 over a at time t, this guy right there, okay? Time is on the x-axis. If we graph this, we're going to get a straight line with a positive slope, and the slope is actually equal to the rate constant in this particular case, as opposed to a first order integrated rate law, which will give us a straight line with a negative slope. So in this case, the slope is equal to the rate constant K. The y-intercept is this guy right down here. This is 1 over the starting concentration, and it'll be a non-zero value. And then you have your slope, and then just the inverse of concentration at some times t. And you can use this to solve problems, and we're about to do that. Now, before we do that, let's take a look at the half-life equation for a second order reaction, because it's different from the half-life equation for a first order reaction. If I go back and show you the half-life equation for a first order reaction, you'll remember that the half-life for a first order reaction is equal to T1/2 is equal to 0.693 over K. There's no concentration. We are concentration independent for a first order only reaction, which is different from the half-life equation for a second order reaction. Let me rewrite that so that it looks a little bit easier to read. That's 1 over K, the rate constant, times the concentration of A. Now, as the reaction goes forward, our concentration of A is going to go down. So if we have a smaller concentration of our reactant A, what's going to happen is you have a smaller denominator. It's still being divided into 1, and so that's going to cause the half-life to increase. So smaller concentration and longer half-life. And that's for a second order reaction. And exactly the opposite. If you have a higher concentration, you have a shorter half-life. Okay? All right, so let's work a problem in second order kinetics. So the rate constant for this second order reaction is 0.690 per molar per second. This is our rate constant. You could tell from the units, because remember that if it's second order, you're going to have 1 less. That's m squared for a second order, and then you're going to have 1 over m times seconds. Your molarity is 1 less. All right, so hopefully that made a little bit of sense, kind of confused me. So how long in seconds would it take for the concentration of A to decrease from 0.970 to 0.380 molar? All right, so the first thing I would do is I would write symbolically the second order half-life equation, just so you know what you're doing. So this is K. This is time plus 1 over the inverse of your starting concentration. All right, so we have a starting concentration. This is A naught, our starting concentration. This is A at time t, and we simply want to know how much time it would take if our rate constant K is equal to 0.690 per molar per second. So I'm just going to plug, well, let's go ahead and solve for time first. So if I'm solving for time, I think a good thing to do, let's go ahead and let's subtract 1 over A naught from both sides of the reaction. That'll get all of our 1 over A naughts on the same side. They'll cancel over here. And then we can divide by the rate constant K. And so that'll cancel it here. It'll isolate time. So that'll give us time is equal to 1 over A at time t minus 1 over A naught, and then we're going to divide by K, and K in this particular, we're going to divide by K. So now all I have to do is plug things in. So this is just going to be 1 over A at times t is 1 over 0.380 minus 1 over A naught, which is 0.970, and then I will divide by 0.690 per molar per second. Okay, so let's do the math and let's see how that works out. So when I do that, it looks like I come out with 2.32 seconds. Well, that's a pretty fast reaction. We're losing about 2/3 of our starting concentration in a period of 2.32 seconds. So now that we've talked about a first order integrated rate law and a second order integrated rate law, let's talk about a zero order integrated rate law. So here is our reaction, and if I were to write a rate law for a zero order reaction, here's the deal. If my reactant is zero order in this reaction, that means its exponent is a 0, and anything to the 0 power is 1. That means that the rate law is actually just rate is equal to K. That's why the units on the rate constant are molarity per second, which you can see right here. We have rate constant units, which are just molarity over seconds. All right, so let me show you what the zero order integrated rate law looks like. Here is A at some times t. It's going to equal negative KT plus the concentration of the starting concentration. So this is your Y value. Here is your M, which is again equal to negative K, and T is your X value, and then A naught is the Y-intercept at B. And if I were to draw the zero order integrated rate law plotted on a graph, this would be just A at times T versus time. You would wind up with a negative slope. The slope would equal the negative of k. The y-intercept would be the starting concentration. And so it has some similar features to the first order integrated rate law, except that we haven't manipulated the concentrations of the reaction at all. We've got just the concentration of A naught, at A at times T is equal to minus KT plus A naught. Now, if I do the derivation for the half-life equation, I come up with, and let me just redraw that a little bit, T 1/2 is equal to the concentration of A naught divided by 2K. That is the derived half-life equation. Now, you will remember that the first order integrated rate law half-life equation is independent of concentration. The second order integrated half-life equation has the concentration in the denominator, and so when the concentration of A naught goes down, the half-life goes up. But in the zero order, it's exactly the opposite. Since A naught is in the denominator, as the concentration goes down over time, the numerator is getting smaller, and so the half-life is also getting smaller. An easy way to distinguish between half-lives of zero and half-life for second order is that for zero order, the lowering of the concentration equals a lowering of the half-life, and in a second order, it's exactly the opposite. The lowering of the concentration equals the raising of the half-life. So go back, you can just scroll back, take a look at the second order half-life equation, compare it to the zero order half-life equation. All right, so let's solve this problem. We know we've got a zero order reaction here. It says how long in seconds would it take for the concentration of A to decrease from 0.830 to 0.320. So here is our integrated rate law. A at times T is equal to minus K T plus the concentration of A naught. And we're going to solve, it looks like, just for time in this particular case. So we're going to do the same thing we did last time. We're going to subtract A naught from both sides. That'll get rid of it over here. We'll subtract it over here, A naught. And then we'll go ahead and we'll divide both sides by minus K. So that's going to give us, I'll just move over here a little bit, time is going to be equal to A at time T minus A naught divided by minus K. And all I have to do is plug my values in. Now just make sure this is a subtraction, that if you're going to do this all in your calculator at one time, just put parentheses around these values. So A at times T is the lower value, that's 0.320 molar, minus A naught, which is 0.830 molar, and we're going to divide that by minus K, and our K value is 0.0210. Okay? And when I plug that in my calculator, 0.320 minus 0.30 in parentheses, and then divide by minus 0.0210, I wind up with, looks like 24.3, and we are in seconds. So that would be my time. So there's an example of using the zero order integrated rate law. You will need to be familiar with all three of these rate laws: zero, first, and second order integrated rate laws, and you'll need to be able to tell the difference between one graph and another. The graph for a zero order integrated rate law, there's a graph for a first and a second order, and I'll go over those in a little bit. Okay, well, let's do it right now. Here's the way this problem is set up. This problem says, I don't know whether my data is for a first order or a second order reaction. So if I were to graph the natural log and it were a first order reaction, I should get a straight line with a negative slope. And I don't. I actually get a curve. This is not a straight line. It's not very curved, but it's definitely not a straight line. It has a curve to it. If I graph the inverse, 1 over the concentration of nitrogen dioxide versus time, and I get a straight line with a positive slope, I know that this is a second order reaction. So this is just a way to use a graph and make the determination of whether a reaction is zero, first, or second order. In this case, it is definitely second order, and that's my reaction. That's the decomposition of nitrogen dioxide to nitric oxide. Okay, so it's a second order reaction in nitrogen dioxide. Okay, here is a way to use graphical data to determine whether your reaction is zero, first, or second order. So you get a set of data, and you don't know whether it's zero, first, or second. Presumably it's one of those. All right, if I graph concentration versus time, this is time on the x-axis here, and I get a straight line with a negative slope, I know that this is a zero order reaction. If I were to graph the natural log of A versus time, presuming that it's a first order reaction, I get a curve. With any kind of a curve, I know that it is not first order. And if I do the same thing with the inverse of concentration versus time, and I get some kind of a curve, then I know it's not second order. So not second order, okay, not second, and not first, okay? We do know that it is zero order, because I got what I expected to get from a zero order reaction. That is graphing A versus time without manipulating the concentration of A. Okay? All right, so let's say I graph my data, A versus time. I get a curve. It's not zero order. So not zero, okay? Not zero. I graph the natural log of A versus time. I get a straight line with a negative slope. Yep, this is a first order reaction. And just to be sure, I graph the inverse versus time. I get a curve, and so I know it is not second. Okay, not second. It is first. It's not zero. All right, so let's go for the next set of data. So I graph my concentration versus time. I get a curve, not zero. Okay, can't be zero, because if it were zero order and I graph concentration versus time, I would get a straight line with a negative slope, and I did not get that. Okay, I graph the natural log versus time, trying to determine whether it's first order, and so not first, because I did not get a straight line with a negative slope. So not first. I graph now the inverse of concentration versus time. I get a straight line with a positive slope. Yep, it's second order. And that's the way to use the graphical representation to determine whether you've got a zero, a first, or a second order reaction. Okay? So let's do one more first order integrated rate law problem, and then we'll call it quits for this video. It's getting kind of long, and I'm getting kind of hungry. So first thing I want you to know is that radioactivity, okay, radioactivity activity is the kinetics of radioactivity operate by first order kinetics. Okay, first order kinetics. As an aside, do you know who coined the term radioactivity? An amazing scientist, one of the most amazing people ever in science. Her name was Marie Curie. And if you look up, it's a very famous picture. It's got Einstein in it, Niels Bohr, Wolfgang Pauli, just an array of amazing people. Marie Curie is right there on the front row, and she coined the term radioactivity. Brilliant, brilliant person, operated at a time when women were not taken seriously in science, and she won 2 Nobel Prizes. Just an astounding person. And in any case, there's also a pretty good movie. It's either on Netflix or Prime called Radioactive. And take a look at it. I enjoyed it very much, but I'm a big fan of Marie Curie. So at any rate, so the radioactive isotope phosphorus-32 decays by first order kinetics and has a half-life of 14.3 days. How long does it take for 95% of the sample to decay? All right, first things first. We are looking at first order kinetics, so we know we're going to use the first order integrated rate law, which is the natural log of A times t is equal to minus k times time plus the natural log of A naught. So this is your first order integrated rate law. That's what you're going to use to solve this problem. So you don't have concentrations here, but what you do have is percentages. So you could actually take any particular total amount to start with. For instance, you could start with 100 grams, 100 molar, whatever it is that you wanted to. And then you would simply take 95% away, and that would be what would wind up over here in as the A times t. It would just be the 5% that remains. So you could do that based on 100. But you know what? There's a simpler number. What is the loneliest amount we could start with? Well, we could start with 1. And starting with 1 has some advantages here. All right, so let's go ahead and put this together. It's not going to be complete. We'll save this, and that's going to be equal to minus k. Now, we don't know what k is yet, but we're going to determine it, and we're going to solve for time. That's what the how long does it take is what we're solving for, plus the natural log, and we're going to just start with 1. All right, so during the course of the reaction, if we start with the amount 1 and 95% of 1 goes away, what's left? Well, if I start with 100%, which is 100% of 1, so 95% goes away, that leaves me with 5%. And if I've got 5% of the original 1 left, that is really just 0.05. Because if I added 95% of 1, that would be 0.95, right? So this is what's left. So this is going to be 0.05, okay? Alternatively, I could just take 5 divided by 100, which would give me 0.05, and this would just be 100 that I would be starting off with, okay? But I think 1 is easier. Why? Why is 1 so much easier? Because the log of 1 is equal to 0. And that term completely goes away when I just plug 1 in there. Now I have less math to do. All right, but I still need the k value. Well, if you remember, the half-life equation is equal to 0.693 divided by k. Well, I have the half-life. They gave it to me in the problem. And frequently you will have half-lives in radioactive type of problems, nuclear problems. And so all I have to do is solve for k. I'm just going to multiply both sides by k, divide both sides by the half-life, and they just switch places. So this will be 0.693 divided by 14.3 days. Okay, and that's going to give me 1 over time, which are the units on my half-life equation. And when I plug that into my calculator, I wind up with 0.0485 per day. So that's just going to be days to the minus 1. Now I can solve my problem for time. I have the natural log of 0.05, and all I have to do is divide by minus k, and my k value is 0.0485 per day. Okay, days to the minus 1. And that is going to give me my answer in days. And it looks like I wind up with, looks like I wind up with 61.8 days. All right, if you had problems with that, just go back, take another look at it. Once you realized it was a first order reaction, we use the half-life to determine the rate constant. That's a common thing that you might encounter in these types of problems.